Today we're going to discuss carboxylic acids. So carboxylic acids have at the end of a chain a carbon that has two oxygens attached to it as well as a hydrogen right here. That can be written in a variety of ways, so you have to be able to recognize it in multiple formats, or you might run into some problems there. To name these guys, realize that it has to come at the end of a chain because carbon already has 1, 2, 3 bonds. See? 1, 2, 3. So it's got to be really only connected to one other carbon. But we remove the E from the chain name and replace it with oic acid. And those are two separate words. So the hard part is remembering that that carbon right there actually counts. So that would be 1, 2, 3, 4 carbons. And that's what makes this butanoic acid. Here I have 1, 2, 3 carbons, and that's propanoic acid. And we always start from the carbon that's in the COOH, which is 1, 2, 3, 4, 5. So it's pentanoic acid, and at the third carbon, that's a methyl. Just like we used phenol earlier, benzoic acid, as you see right here, is a special case. So benzoic acid is going to be with a COOH, and it doesn't matter where that OOH is, it's still benzoic acid. And the carbon that it's attached to in that phenyl group is number 1. So if this is the case, 1, 2, 3, 4, or 1, 2, 3, 4, that is 4-methylbenzoic acid, or paramethylbenzoic acid. That's another way to say that. And again, it doesn't matter where that COOH is, that's number 1, 2, there's number 3, so that's 3-chlorobenzoic acid. Okay, just as a reminder, this is how we end up getting these carboxylic acids. If we start with using a primary alcohol, we can oxidize that to an aldehyde, which further oxidizes to a carboxylic acid. Or we can just start with the aldehyde, that's totally fine too, and you'll get a carboxylic acid. Just as a reminder, we cannot do that with ketones. Okay. Now, one of the cool things about carboxylic acids is their polarity. And if you think about this, carbon's sitting here sort of tucked in the middle of two oxygens that are pulling its electrons away from it. Well, that means that it's relatively positive. That also means that the hydrogen itself is relatively positive. And that's what makes it an acid, is that this hydrogen can come off, which we'll look at in just a second. But because it has an OH, this guy can hydrogen bond. And it can actually hydrogen bond to molecules of itself, and easily over here or here. So if you want to think of that as two locations where it can hydrogen bond, that's pretty cool that it can do that. And you could actually have dimers of this sort of connect and form sort of a bigger type of dimer. But this isn't an actual covalent bond, so keep that in mind. These are intermolecular forces. So probably more likely what would be going on in a large amount of this is that you would have hydrogen bonding happening between molecules, just at two different sites. So, for example, this oxygen can connect to that hydrogen, and this hydrogen can connect to that oxygen. So they're going to have high boiling points, even higher than what you have in alcohols, because remember, intermolecular forces are the things that bind molecules to each other. So they don't have necessarily, it takes more energy to get them out from each other or pull them apart from each other. And that's what boiling points are doing, is you're pulling molecules apart from each other. These small carboxylic acids will dissolve well in water. But again, if you have too much of a nonpolar carbon chain, it still is not going to dissolve very well. Okay, so that's sort of a review in reality of what we've done so far. So let's look at how a carboxylic acid can react as an acid. Keep in mind that in equilibrium, what that kind of means is this goes back and forth and back and forth and back and forth if you're a molecule. But it more also means that there's a certain population of molecules that are on this side and a certain population of molecules that are on this side. So equilibriums can be primarily on this side as your product. You could have it primarily as this side as your product, or you could have it even or generally even. What we find with this equilibrium is that really it sort of stays to this side. But a little bit of this carboxylic acid will donate its hydrogen over here, if you want to think of it that way, leaving behind a COO minus and an H3O plus. We call that dissociation in water. So it will, in a little bit of it, will dissociate in water. However, if you have a strong base, such as NaOH, remember this is the same thing as saying Na plus and OH minus, and I don't care if that's Na, K, Ca2, whatever that may be. That can be, that's just sort of a counter ion, it doesn't really make a difference. But this is OH negative. And an OH minus says, hey, you got an H plus over there? Let me go grab it. And it does react. Notice this is not a reaction going back and forth. It comes and grabs this, and it goes to water. And you're left with a COO minus. If you dry out the water, the Na will associate with that. So this is known as a carboxylate. And if you want to really consider it, it's a carboxylate salt. Now, how does this COO look like? Because it kind of feels like, I don't know, saying moo, but it's coo. But here we've got C, double bond O, and then it just means that this oxygen right here has electrons around it, and that's got a negative charge to it right there. Okay, thanks.